Today, what we're going to be focused on the most is identifying the factors and how they relate to reaction rate and how it relates to concentration versus time. There's some Utah standards that we're covering. Sapling 8.1 will open at midnight tonight. Need to start working on that, and quiz 8.1 you should have done. And we will do the factors. So here are the factors that we're going to be talking about as far as reaction rates. They depend on an effective collisions between particles, so we're going to be looking at the nature of reaction. If two things will react, okay, that's part of, is it going to happen? Okay, concentration. If I have a concentration here at the school of a couple thousand, the chances I meet somebody that I like, probably pretty high. If I go to Lima, Montana, where graduating class is 5, probably not so much. Okay, so concentration does matter. Surface area. The bigger the surface area, the easier it is going to be to hit it with the right amount of energy for a reaction to take place. Pressure. I think about, you know, a lot of the movies they said that they have been made that say, oh, so-and-so needs to marry before their 21st birthday or they lose their inheritance, blah, blah, blah. So there's a lot of pressure to get stuff done. So they're working really hard to get it done. Temperature. The higher the temperature, the faster things move, the chances of collision being effective are more. And then the presence of a catalyst. That's the matchmaker, getting them together. So we've got a few things that will affect reaction rate. We're going to be testing a few of these as we go. Let's talk about this. I'm going to. All right, so let's go forward here. He talked about a couple things. Temperature. We want to raise the temperature if we want to have the reaction go faster. He talked about particle size. We want smaller or powder instead of bigger particles because that'll give us more surface area. More surface area means faster reaction. So as we go, we want the smaller the particles, the bigger, the faster the reaction. Concentration, we want more solute in our solvent so that we have a lot more things to choose from. Okay, so concentration, that's where he shoved all the people in the room into the school. A matchmaker is a catalyst. We learned it this way, where it's just lowering the activation energy, but it can actually look like this, where the activation energy is lowered, but it has several different steps in between. So let's talk about effective collisions. An effective collision is basically between two reactants, but they've got to be correctly oriented. So if you think about it, in order to have an effective collision to get a date, you've actually got to face them. You can't go up to somebody and have their back to them and say, hey, do you want to go to the date or dance or whatever? They're not going to know who you're talking to, right? So you got to have correct orientation, and you've got to have enough energy. Because if somebody comes up to you to ask you to a dance and they're like going, gee, oh my gosh, and don't have enough energy to actually ask you, it's not going to happen, right? Okay, so the other thing is a catalyst. A catalyst is a matchmaker. So here we have effective and ineffective collisions. The other is a catalyst. A catalyst is somebody that gets two things together, or something that gets two things together. Catalyst is like a matchmaker. That's the easiest way to remember it. But now, besides a catalyst, we've got an inhibitor. This is somebody that sort of doesn't want you to get together. Sort of like your mom and dad saying, you're only 16, you're not going steady, there's a whole bunch of your life left to go, you need to date others. They're the inhibitor, right, to having that guy that you want or that girl that you want for forever. Okay, so you've got effective collision, catalyst, and inhibitor. An inhibitor is basically the opposite of a catalyst. Now, if you go on to 1120, we talk about catalysts being enzymes, and enzymes help our body to work and help reactions to work through your body. Okay, we okay? Got main gist? Okay, so then we've got homogeneous and heterogeneous catalyst. Homogeneous means it's in the same phase as the rest of the reaction. So if I have a liquid that's going through reaction, then I need a liquid catalyst to be a homogeneous. If I have a solid that I put in, that would be a heterogeneous catalyst. So it's all about the phase when we're talking about homogeneous and heterogeneous. Homo meaning the same and hetero meaning different. Okay, so let's look at these reactions. We need to be able to look at a reaction and be able to say, okay, what's going on here? Is the reaction rate going to be quick? Is it going to be slow? Is it not going to happen at all? So the first one, we've actually seen this reaction when when I was showing you the different types of reactions. This was a synthesis reaction with potassium iodide and lead nitrate. And I poured the two clear liquids together and we got a yellow solid that came out. It was a yellow canary solid. Did it happen fast? Did it happen slow? It did happen because I just told you it did. So what did it happen? Did it happen fast or slow? It happened fast. I poured it and it just went boom. And the reason why is, look, we've got two ions, and ions want to come together and make a zero charge. So they're attracted to each other because opposites attract. So that one's fast. What about number 2 there? The bromine ion and the iodine ion. What do you think about that one? Fast, slow, doesn't happen? Well, let's look at it. We've got a bromine that's a negative ion. We've got an iodine that's a negative ion. And it says it makes a bromine iodine -2 ion. Is that something that wants to happen? No, we want, if I have the same charge, they're going to repel each other. They're not going to be wanting to come together. Okay, so they're going to be repelling each other. They're not going to want to go together with a -2 ion charge. Not going to happen. So this one won't react. Let's look at this next one. This is the one we did in a straw when we were working with the gas laws. And we dipped one in one compound and one in another, and then we put it in the straw. Remember that? What happened in the center of the straw? It got a white cloudy mixture. That white cloudy mixture is that ammonium chloride. Did it happen fast? Did it happen slow? Or did it not react? It was not real fast. I would call it slow. It took a minute for the gases to get together, but when they did, then they kept reacting. Okay, this one down here, calcium oxide, or carbon dioxide giving us calcium carbonate, which is lime. So I've got a white solid that I'm putting carbon dioxide on, and it's making another solid. Is it going to be fast, slow, really slow? Won't happen. What do you think? Give me a guess. It's really slow. Okay, it's really slow. I've got a solid and I'm trying to put a gas through a solid. The only thing that's going to react is the outer shell of that. Okay, so we have a reaction rate. And over time the reaction rate slows. So we start a race, we're going really, really fast, and then we run out of energy, right? So explain the behavior. At first, I have a lot of stuff that's going to mix together and make couples. So if you think about it, in Utah, we have a lot of people, 18 to 21, they go to college and they find the one and they get married. And if you wait around until you're 30, 31 in Utah, good luck trying to find somebody, right? But if you go somewhere else in the United States, 30, 31 is where most of them are getting married. They're not getting married down here. They're getting married on 30, 31. So what happens with reaction rate is when you have a lot of things that can combine, it's easy to get a reaction going fast. But when you have the last 31-year-old in Utah, in Logan, and the other one in Provo, and you're trying to get them together, it's going to take some time. So it's a slow process. Does that make sense? At first it was fast, but then it slows down. Okay, so we're going to do a demonstration right here. Will somebody grab the lights real quick for me? Just somebody go turn the lights on. Thanks, Jonathan. Okay, I'm going to pause the video while I do this. We're going to talk about, go on to your lab now. We're done with the lecture for today. While you're getting your lab out, I'm going to go put this away and to tell you a couple of things. If you'll notice, the big ones are still going. What happens when I put a big chunk of dry ice in regular water is it actually forms a coating of ice around this carbon dioxide, even in hot water. And so it's harder for it to, the water to get to the carbon dioxide. So there's little holes in which it's reacting, but it's encased in ice. My hot water is gone. Dry ice is gone. I still have some lingering in my cold water, right? Okay, so what we're going to be doing is we're going to be doing a lab with rates. Rates just means how much something changes over time. So if I were to travel 300 miles in 5 hours, I'd be going about 60 miles per hour. Miles divided by hours. We already know this rate. But in chemical, instead of using miles and hours, we use a unit of either moles or grams versus time. So in your head, and if you want to be brave and volunteer, let me know what you think. How fast would a mole of iron rust? What would the units that I would use? The first one would be moles, but what would I divide it by? What would I divide that by? And this is in your lab. How fast does it rust? How fast does something rust? Think it would be hours? It says 0.5 moles. That's a lot of moles. If you look at a mole, 55 grams. So 23 grams rusting every how much of a mole? So half of the mole that I have would be rusted. So how fast do you think that would happen? Days is a little bit fast. So weeks or months would probably be okay. So let's put months. Okay, we're going to be doing 3 different experiments. You and your partner have got to figure out how you're going to tweak it. I tweaked these up here by changing the temperature. They've both had stirring rods in them. I used about the same amount of dry ice in each of them. You're going to be messing with temperature, concentration, and particle size. Those 3 things. That's it. Okay? But we'll be doing 3 different experiments. Those things are on the right-hand side down at the bottom on your front page of your lab. Down at the bottom on the right-hand side, there's also this thing that says concentration, particle size, and temperature. I'm going to be showing you each experiment. As I do each experiment, I want you to write down, does it fit under particle size, concentration, temperature, and maybe underline the one you think you want to use it on, the one you think it would work the best on. And when we're all done, hopefully you only have one underlined in each one, because you're going to have to choose an experiment to do concentration, an experiment to do particle size, and an experiment to do temperature. You've got to use all 3 experiments. Okay, you can't just use one experiment and do all of them on it. Okay, so let's talk about the first one here really quickly, and then we'll go do it. So this first one is a reaction with sulfuric acid and sodium sulfite. When you react those, you get sulfur dioxide gas coming off and sodium sulfate left, and a little bit of water. We're going to be doing this in a Petri dish. And what we're going to do is these colored places on the Petri dish are our universal indicator. We'll put 1 drop inside, 1 drop on the lid. The one on top of the lid is our sort of control. So we can see when the one inside starts to change. Because sometimes it's hard to see change if you don't have something to compare it with. So 1 inside and 1 on the lid. Opposite that, on the other side, is where we're going to put on top of each other the sodium sulfate, or sodium sulfite, and the sulfuric acid. The minute I put those on top of each other, I put the lid back on, and I wait for that sulfur dioxide gas to get to the other side and change the indicator. I'm going to time that time. Okay, so let's show it, and I'm going to start that. Remind me to turn that off again. So on the second one, we're going to use magnesium ribbon. On the first one, I gave you the chemical equation. On this one, I didn't, because I think you can do it by yourself. Because we're using magnesium ribbon, which is what? Mg, plus hydrochloric acid. What's that? HCl. Yields, what do you think it's going to yield? MgCl2 and H2. Then you'll have to balance it. Okay, so we're going to have a well plate for this. We're going to have some HCl, we're going to have some magnesium ribbon that you're given, and some distilled water. So again, I'm going to stop this. I'm going to turn that back on. So the next one we're going to be doing is a seltzer tablet with water. And we're going to be doing this one outside. So you're going to be prepping it inside, but you're going to be going outside. You're going to be measuring 2 things with this one. The height, how many bricks up it goes, and the time, how long does it take. Okay, you'll get a film canister, and it has marks 1/4, 1/3, and 3/4 on it, but you could go a little bit under for a third. You could go, you could make your own marks in between if you wanted to. You'll be given 2 tablets that you can divide into 4 on one tablet. You can divide each tablet in half. You could crush the tablet. You could put more in for concentration. So you can do particle size pretty easy on this one. You could also change the temperature of the water on this one. Okay, so I'm going to show you this one. I'm going to turn this off. Oh, let's go back to here really quickly. You have one of these to test each of them. So go ahead and turn the page. Before I allow you back in lab next time, you need to have all three of these ready to go. You need to tell me the balanced equation. You need to tell me the problem. This is easy, guys. You look at the top and you say the effect of concentration on reaction. Oh, the problem is, what is the effect of concentration on reaction rate? Okay, that's not hard. Your hypothesis is, what do you think it's going to be? What do you think is going to happen? Okay, what is IV? Independent variable. What is that? That's what you are changing. So what are you changing? What is DV? Dependent variable. That's what changes because of what you change. So that should be your time almost all the time. And for the film canisters, it will also be the height of the bricks. What are your constants? The things you're holding steady. So the Petri dish, the amount of universal indicator, the temperature of the water, whatever I'm holding steady, it goes constant. Procedure. You need to write your procedure so that you could hand it to a neighbor. Your neighbor could read it and know what to do without asking you any questions. Okay? Use your data table. Say this is like trial, and it's not going to write. Trial 1, 2, 3, 4. For instance, on the first one when we did the sulfuric acid, and maybe I'm using that for concentration. You don't have to. I'm just showing you how you could set it up. Na2SO3 and time. So maybe I choose 5 drops and I go 4, 1, 2, whoops, let's do 3, 2, 2, 3, and then 1, 4. So over here I can say, with my universal indicator, drop 1 on the outside of the Petri dish, drop 1 on the inside. Opposite that, use the drops in trial 1 to drop on top of each other. So I don't have to have all this in here. And then when I get to the bottom, I say repeat using trials 2, then 3, then 4. So I don't have all of this. You do not have to use all 10. You can use more if you need to. Okay, so I should have this part, and this part set up. When I'm done, remember on this side, my IV usually goes along the x-axis. My dependent variable usually goes on the y-axis. Okay? But I need you to have the first 3 set up. Once you've got those 3 set up, you and your partner come up, I check it off, and you're able to go back in lab. So before we leave, I would talk to my partner and say, okay, which one are we doing? Get my procedure set up, get the lab data table set up as best you can. Okay, go.